At the end of this video, you should be able to describe how a protostar becomes a star. Chapter 30, Section 2, Stellar Evolution. Classifying stars. Plotting the surface temperatures of stars against their luminosity, or total amount of energy they give off each second, reveals a consistent pattern. The graph that illustrates this pattern is the Hertzsprung-Russell diagram, or HR diagram, a simplified version of which is shown in Figure 1, or on the screen here. The graph is named after Einar Hertzsprung and Henry Norris Russell, the astronomers who discovered the pattern nearly 100 years ago. The temperature of a star's surface is plotted on the horizontal axis. The luminosity of a star is plotted on the vertical axis. Astronomers use the HR diagram to describe the life cycles of stars. Astronomers always plot the highest temperature on the left and the highest luminosities at the top. The temperature and luminosity for most stars falls within a band that runs diagonally through the middle of the HR diagram. This band, which extends from cool, dim red stars at the lower right to hot, bright blue stars at the upper left. This is known as the main sequence. Stars within this band are called main sequence stars. The Sun is one example of a main sequence star. Star formation. A star begins in a nebula, a cloud of gas and dust, such as the one shown in Figure 2, or on the screen here. A nebula commonly consists of about 70% hydrogen, 28% helium, and 2% heavier elements. When an outside force, such as the explosion of a nearby star, compresses the cloud, some of the particles move close to each other enough that they are pulled together by gravity. According to Newton's law of universal gravitation, all objects in the universe attract each other through gravitational force. This gravitational force increases as the mass of an object increases or the distance between the two objects decreases. Therefore, as gravity pulls particles closer together, the gravitational pull of the particles on each other increases. This increase in gravitational force causes more nearby particles to be pulled toward the area of increasing mass. As more particles come together, regions of dense matter begin to build up within the cloud. Protostars. As gravity makes these dense regions more compact, any spin the region has is greatly amplified. The shrinking, spinning region begins to flatten into a disk that has a central concentration of matter called a protostar. This heat energy causes the temperature of the protostar to increase. The protostar continues to contract and increase in temperature for several million years. Eventually, the gas becomes so hot that its electrons are stripped from their parent atoms. The nuclei and free electrons move independently, and the gas is then considered a separate state of matter called plasma. Plasma is a hot, ionized gas that consists of equal number of free-moving positive ions and electrons. The birth of a star. Temperature continues to increase in a protostar to about 10 million degrees Celsius. At this temperature, nuclear fusion begins. Nuclear fusion is a process that occurs when extremely high temperature and pressure cause less massive atomic nuclei to combine to form more massive nuclei, and in the process, release enormous amounts of energy. The onset of fusion marks the birth of a star. Once nuclear fusion begins in a star, the process can continue for billions of years. A delicate balancing act. As gravity increases the pressure on the matter within the star, the rate of fusion increases. In turn, the energy radiated from fusion reactions heat the gas inside the star. The outward pressures of the radiation and the hot gas resist the inward pull of gravity. The stabilizing effect of these forces is shown in Figure 3 on the screen here. This equilibrium makes the star stable in size. A main sequence star maintains a stable size as long as the star has an ample supply of hydrogen to fuse into helium. At this point, you should be able to Describe how a protostar becomes a star.